Good afternoon. We are back. We've got a bit of an impromptu session at the moment. The skies have cleared wonderfully well. Just looking through my skylight, no clouds. So Russell messaged and asked if he could do another session and if we could share the sun live streamed with everybody. So I'll just bring Russell in. Hi, Russell. How you going?
Hi, Mark. Doing very well, thanks. Enjoying some cloud-free skies here.
I know. It's been a while, hasn't
it? What a difference a day makes.
I know. Yesterday was cloudy and poor weather,
and
rained most of the night.
Yeah. Too risky to have set up the solar scope for...
not worth the risk. Well, we had, you were vindicated because Noel was testing his equipment yesterday evening and up in Bendigo, and he had it on the moon and it went dark. And all of a sudden the skies opened and thankfully his equipment was okay. But just not worth the risk, is it?
Absolutely not, mate. And for everyone listening, water is one of the worst contaminants for optics. Particularly doublets and triplet lenses that can get between the elements and really mess things up.
Now, I'm just going to pop this up. It's going to cover my face, but that's okay. So the equipment that you're using today is the Lunt 100mm scope. It's on a Skywatcher EQ6 mount.
Yep.
And the camera is a Woe ASI 174mm.
MM stands for monochrome.
Monochrome. There we go.
White, basically.
I'll get there eventually.
All right.
Now,
no worries.
Have you got it all ready to hook up to the screen for us?
Yes. There we go.
Oh, you'll have to share that one with me.
Yes.
You have to share it.
Of course I do. Yes, I'm just far too
eager.
Correct. And application window. And how many bods have we got with us so far?
We have 55 people wanting to see the sun.
Oh, that's
there we go.
And ladies and gentlemen, ask your friends to join in. Come on, more the merrier.
Yes. Share the stream on your feed and tell everyone they can have a look at the sun live stream. So the sun that's
free.
Yep.
Okay, so shall I start?
Yes, go for it. Get started.
Well, ladies and gentlemen, thank you very much for joining in today for this absolutely live demo of the sun through the ASV's 102mm solar telescope. So I've pointed the telescope at the sun, and crikey, where is it? It's somewhere there. So I can guarantee you that it is there. But however, you notice up here where my mouse is, or my pointer is pointing, I've got all the settings turned way down. So what I'll do is I'll just turn the gain up and see what happens. And I'll turn the exposure up as well. Okay, still no sun visible. So what I'll do is I'll just move around a little bit and see what happens.
I can see some brightness in the corner there, Russ.
Top corner, yes. I suspect the sun will be there. So we're going from absolute beginnings here. I'll just adjust that focus a little bit. So about there. Oh, wow. And one has to think, you'd think the sun would be the easiest thing on earth.
It's big enough and bright enough. Russ, Jen says to take the cap off.
Oh, of course. No, it is off. It is off. Just pulling the leg there. Now the sun is around here, folks. Just bear with me. I'll just crank up the rate a little bit. So as you can see, this is from absolutely the start of our demonstration.
Now,
anyone who's used the laptop in sunshine will realise how difficult it is to see the screen. So I'm going to cover up.
Russ is going undercover.
Undercover,
Now,
yep.
now while you're doing that, Russ,
Yeah.
we should probably talk about the dangers of looking at the sun. The old don't do this without the correct equipment because you have two chances, left eye and right eye.
Absolutely, Mark, and that was one of the key points from my talk yesterday. So yes. Observing the sun can be very dangerous, extremely dangerous to the eyes, and dangerous to your optical equipment as well. But of course, eyes far more important than that. So if you have any doubts about the equipment that you are going to be using to observe the sun, don't do it. Only use equipment that you are 100% confident is safe for solar viewing. If you have any doubts, well, contact me or someone within the ASV, me preferably, being the solar section director, just to have a chat over the safety of the equipment, because we do not want the eyes to be damaged.
No, we definitely don't. How are you going there, Russ?
Still struggling.
It's all right.
Right.
So bear with us. Russ is just trying to get things. So what was that?
I can guarantee the sun is there. I've got that. Right, so I'm just going to do a manual move.
I'll let you know when I see it.
Right.
Oh, there we go. Oh, we had it. It just popped away for a second. Oh, it's right there. Just on the edge there, Russ. It's just on the edge.
Just on the edge.
Yeah, it popped in quickly, but then you popped it back out again.
Come on, son. It's there somewhere.
While you're doing that, Russ, we have a question. I can answer this one. So
yes.
I'll answer this one while you get it lined up. So Wanda wants to know, even using proper solar equipment, can you look directly through it to see the sun, or would you always connect it to a computer to view on screen? Wanda, you can actually look through an eyepiece connected to this particular telescope. It's quite a sight to be able to look through this telescope and see the sun, knowing that you're not going to go blind. I've even put my phone up to it and taken images of the sun through the eyepiece. So it's definitely safe to do when you're using this particular telescope visually without just looking at a computer screen. But unfortunately, at the moment, we can't get up to the areas where the telescope is. So this is the best that we can do for you by showing it to you on your computer screen.
I guarantee the sun is there.
Yeah, if I'm looking at my screen there, Russ, it's a bit to the left. So it was to the left. I'm not sure what direction that would mean you move your telescope, but when I'm looking at the screen, it was off to the left-hand side. Well, that's a good question. Another one from Wanda. Do members have access to this scope? There is a 60mm version. 60
available for loan. Yes, and it's out on loan.
So yes, it's out on loan at the moment. You've got to be a member of the ASV for quite a while, and you have to be trained to use it. There's people lined up to be trained to use it, and I actually chucked myself on that list yesterday, didn't I, Russ?
It's very simple.
Yeah.
Straightforward. Come on, son.
Oh, it's getting bright there.
Yeah. Now I have
to say, it's down the bottom now. Looks like it's down the bottom there. Oh, there we go. Got the corner of it.
Top there, eh?
Yeah, it's top left.
So I can turn the gain down now, and it will disappear. But I'll tell you what, come on, you can do it, right? Come on,
it's coming.
You can do it. You can do it. I've got the gain too high, actually. It is there.
Right. Yeah, it's there.
The sun should be. I've got a little.
Oh! We just had it. We just had it, Russ. It just went flying across the screen.
So unfortunately, I can't see the screen and do what I'm doing here simultaneously. So our field of view is only about the size of the sun, so we don't have a lot of margin for error there. Gee.
Yeah, we did see it. It came in and out really quickly there. It went from one side to the other. Oh, there it is. There we go.
Wow. Oh, that was a bit of a rookie error. Never mind.
Oh, it's gone again. it's up the top. There we go. Got it in there now.
Had my screen far too big.
There we go. Okay, that is the sun. Have a look at that. Doesn't look like much at the moment, but Russ is going to play with the.
There we are.
There we go.
So there we are. There's the sun. I'm going to get my towel over my head as well. So I've cranked the gain right up, and whilst we've got the gain cranked up, let's see what we can see around the edge. Look for any prominences. And
none.
There aren't very many today.
No, very quiet today.
Surprising, really. There were a couple of small ones earlier.
No, I can't see any there at all, Russ.
I will just hone the focus. Just focusing now.
Yep.
Focus is pretty important. And we're pretty close to good focus there, and you can see there's a little one just here and another bump up here. I'll up the gain a little bit to make them. So they're very, very small today.
They are very small, aren't they?
But however, we that's what we get. So let's have a look at the surface of the sun. Now this is a special surface of the sun we're looking at. It's called the chromosphere. So it's a layer of the sun that shines in the light of hydrogen, that beautiful red light of hydrogen. That dazzling sun that we see in the sky today, that light is coming from the photosphere. So there are various surfaces of the sun, and the sunlight that we see is from the photosphere, and just a little bit above it, probably 10,000 kilometers above it, is a cooler layer called the chromosphere, which is far fainter, and naturally the brilliance of the photospheric light completely obliterates any contribution from the chromosphere. But however, we're looking at the chromosphere here, so let's turn the gain down. Whoa, there we are.
Is there some activity on the side? Is there some activity there, Russ?
Absolutely, right here. Yep.
Yeah.
Now, also, ladies and gentlemen, you can see that the sun is not quite evenly illuminated in this stream, and I hope it's a smooth stream for you. So a beauty of the solar telescopes is they have a tuner. So I'll just crank the tuner in and out a little bit just to try and even up the illumination across the sun. So just to make it a little bit smoother, there we are. I reckon we've just about got it there. A nice
looks
even
good
across the sun. Because these telescopes only allow a tiny region of light through, and the tuner helps to just move that that band of light along a little bit. So let's focus on this area here. And I can do that just by using my my mouse and drawing a little square around it. So effectively we're zooming in. Here we are, and I can zoom that up. Now it looks a little bit yucky at the moment because I haven't selected appropriate focus, and need to adjust the focus. Focus is very important for these features. So I'm focusing now, and there we are.
All right, so we've got a couple of questions, Russ.
Yeah.
So Matt wants to know, have we started a new solar cycle?
We just have. Yes, that's a very good question, Matt. NASA have said to us that the middle of the last cycle, which was cycle 24, was last December 2019, and now we've started officially the new cycle, cycle 25. So therefore, in fact, we have a new sunspot today. Has a number associated with it, which is AR12773, and it's a sunspot of the new cycle, cycle 25. Now, during solar minimum, there are some old spots visible and some new spots from the new cycle visible simultaneously, and there's a way of checking which is which, but this is definitely a sunspot of the new cycle, cycle 25. And you can notice that lots of structure around it. Now, I should point out that all that movement is really the Earth's atmosphere. Okay, so this is not seeing the actual movement of features on the sun, but every light and shade that we see on the screen are features in the sun's chromosphere. But that little white area that is called an active region, because magnetic fields are connecting together and releasing some energy, which causes the region to appear a little bit hotter compared with the other regions around it. And hotter generally means whiter and lighter. So this is an active region associated with a tiny sunspot. Now, it's ironic that hydrogen alpha is not particularly good for sunspots, because sunspots tend to be more in the photosphere below. But if over time this sunspot grows bigger, then it most likely will extend into the chromosphere and become visible in this telescope.
So that's a question that we've got is Vicky wants to know, what is the activity? So what are we looking, that you've just described exactly what we're looking at, haven't you?
Yep, so okay, so the sun provides us with heat and light and of course gravity to keep the Earth and the planets in orbit. But the sun is also a huge magnet, and the sun's solar cycle is really a magnetic cycle, a cycle of changing magnetic activity. So during solar minimum, the sun's magnetic activity dies down, and sunspots are a direct result of the solar magnetism. So fewer sunspots means less solar magnetic activity. As the solar cycle heads towards maximum, then there's more magnetic activity, and hence more sunspots and more flares and more explosions on the sun, more coronal mass ejections, and hopefully more auroral activity. Now, the light and shade we are seeing, okay, so there's our active region just here. Now, this is cranked up quite a lot. What I think I will do is just reduce the magnification just a little bit.
Oh, there we go. That's good.
Our sun in all of its glory. So I should say all this light and shade. A little bit too much noise there. I'll just reduce that down a little bit. See that? I can make the sun disappear. And there we are. I'm just increasing the exposure. And you can see the histogram down here responds to that. And if I was taking a video photo of this, I would generally have the histogram about in that region.
That looks really good there, Russ. That's quite a nice crisp image, isn't it?
Well, I shall leave it there. So once again, I will just zoom in a little bit onto this region here.
So while you're doing that, we have another question. Kane wants to know, how far away is the sun?
Another very good question. And look, experienced people like myself tend to forget that this is information that is not always in people's memories. But the sun is 150 million kilometers away from us. 150 million kilometers away from us. And of course, we should remember that the Earth is in orbit around the sun. So the sun is effectively stationary as the Earth orbits around it. So we really should say the Earth is 150 million kilometers from the sun. Well, a reasonable distance. I wouldn't want to run that far. Ha ha.
Here's a question for you, Russ.
Yes.
What elements correspond to the spectral lines in the histogram?
All right. Well, I've just done a little bit of an imaging trick here. I've turned this thing called gamma right up to maximum, and what that gamma does, it increases the contrast visible, but also it means that certain levels in the values that the camera is sending to the computer are missing. So that's what these black things are. They're actually values in the grayscale which are missing. So I can show you that by just turning the gamma value down. And there we are. Look, all those lines have disappeared. But you notice that the image has lost a little bit of contrast as a result of that. So for visual work, obviously, I'd like the contrast to be as good as possible so that we can see features. And please remember that these features are pretty low contrast. The contrast meaning the difference between light and shade is not that great. So, that's true visually as well as photographically. So I'm just telling the system here to maximize the contrast available to this live stream so that these features are more easily visible. And there we are.
That's beautiful. That looks really good, Russ.
And once again, emphasize, ladies and gentlemen, all this structure is actually on the sun. It's not an artifact of the camera or the equipment or the Earth's atmosphere. All this structure is structure on the sun. And from point of view of comparison, I reckon the Earth would fit quite nicely in this little circle I'm drawing on the screen here. Earth would fit quite nicely within that. And what is fully beautiful, and I'll just leave this whilst I'm talking, you can see there's it's not just light and shade, but there's actual structures. You know, there's some curly bits here around it, and it is quite marvelous to see with our very own eyes through this video camera. Now, I really wanted to explain what these structures are. So remember, the sun is a very hot ball of gas, and hot gas rises. Hot gas is less dense, so it tends to rise against denser material, but as it rises, it cools down. So all these lighter areas like this, and especially that area here, are slightly hotter columns of gas rising up. As they rise up, they cool down and they turn into these slightly darker, grayer areas, which is cool gas descending back down into the chromosphere. And so that's why we see this structure. Slightly hotter gas rising, and really we're only talking about a few hundred degrees Kelvin difference in temperature between the hotter gas and the cooler gas. Hotter gas rises, cooler gas sinks back down, and of course then heats up again and rises up. So we get this constant flux of hot gas rising, slightly cooler gas settling back down again. So
now, we have some more questions, Russ.
Excellent.
What are the different filters used for solar observing? Some produce yellow, white light, some are better for prominences, etc.
Yeah, well, really, as far as amateurs are concerned, the hydrogen alpha telescopes are the best for observing features on the sun and prominences because hydrogen alpha telescopes are not quite mass-produced, but quite a few of them are produced annually. And for an amateur, that's the best piece of equipment to get to see features on the sun like this, what we're seeing now, and prominences. You can get telescopes that will detect the lines of calcium. And so we sometimes see images taken in calcium light, and these are colored blue because that's where the calcium absorbs or emits light in the blue part of the spectrum. And so these images are colored blue to reflect that. And I'll say this is really a monochrome camera that I'm using, so we're not seeing the rich reds of hydrogen alpha. But in fact, if I was using a camera that picked up red and showed it as red, the image or the view wouldn't be nearly as impressive as this, because color tends to confuse and distract our sensory systems. And grayscale that we're looking at here is particularly good for picking out light and shade. So, and there's the so-called white light filter that fits with just a bit of shiny plastic, aluminized plastic, fits over the front of your telescope, whether it's a refracting telescope or a reflecting telescope or even a pair of binoculars. That white light filter just cuts out all wavelengths of light equally, and so you see a white image. But sunspots show up very nicely indeed as very dark areas.
So, I'm kind of tempted to grab the Dobsonian and chuck it outside and
that's right.
Filter on, because that would appear as the sunspot for me right now, wouldn't it?
It would, a tiny little black spot, yes, tiny little spot right here.
Right. We have another question here for you, Russ.
Yep.
With the rotation of the sun being approximately 27 days at the equator and 31 days at the poles, why do we not see this being similar to Jupiter, or can it be seen at different wavelengths?
Not quite sure what the...
So talking about the rotation of the sun is different at the different points. So why, I'm assuming the question is, why do we not see that happen on Jupiter? Might leave that one for.
Okay, well, the Jupiter is called a gas giant, but it will have inside it a solid mass, which will rotate at roughly 10 hours. But the gases in the atmosphere of Jupiter actually have different rotational periods, and so there's really not one specific rotation period for the cloud belts of Jupiter either. So I'm not quite sure whether that helps at all.
I hope it does. I've got an easier one for you.
Oh, thanks.
Stuart wants to know, what do you feel is the best camera for this type of imaging?
Well, for hydrogen alpha imaging, you definitely need a camera that has extended its sensitivity into the hydrogen alpha region. Commercial digital SLR cameras, if you're thinking of that, well, they have a filter built into them that cuts out ultraviolet, but also infrared. But unfortunately, the infrared filter cuts a little bit of the visible red light out as well, which actually impacts on the hydrogen alpha wavelength. So taking images of the sun through hydrogen alpha telescopes with a normal digital SLR doesn't provide a very impressive view at all. If you're talking about sort of professional videos and what have you, pretty much any a video camera that is designed for astronomy will provide views like this. But of course, it's actually the front end, the hydrogen alpha telescope, that is providing these beautifully rich and detailed features on the sun. But there's plenty of skills and experience in the astrophotographic group that you can tap into for camera selection for your particular purposes. So I'll finish off by saying this particular camera here is not particularly good for nebulae and what have you. It's good for close-up views of the sun and of the planets, because the chip is relatively small, and roughly it's you can see a field of view of about 1/2 of 1 degree, which is what the diameter of the sun is viewed in our skies. But as I'm talking, I'm just enjoying these beautiful views.
We've got another one for you.
Sure.
Does the sun's gravity have any impact on our moon?
It will have a slight impact on our moon, because remember, gravity goes to infinity, but because the moon is closer to the Earth, and therefore the moon is orbiting in the potential well provided by the Earth's gravity, but nevertheless, Earth-Moon system is nevertheless orbiting within the potential well provided by the sun. So the sun will affect the moon's motion ever so slightly, and this effect has to be taken into account when calculations involving the moon's orbit are taken out. For example, an occultation of a star or of a planet by the moon, the timings and eclipse timings as well, solar eclipse timings, have to take those small effects into account for very accurate predictions. So yeah,
wonderful.
The moon's motion, but the moon's motion is dominated by the Earth, because the Earth is so much closer to the moon.
I have another one for you, Russ. They're coming in.
They're excellent questions.
Have modern large observatories got the ability to see the surface of stars outside of the solar system?
They do have, yes, and 2 or 3 of the largest stars have had their surfaces observed. Betelgeuse, Betelgeuse, whatever you want to call it, Alpha Orionis, the red star in Orion, has had its surface observed, and I think Antares and Mira, which are all red supergiants, being relatively close to us and relatively large, have had their surfaces observed, not at the resolution we're seeing right now, but nevertheless large scale structures have been observed on them, like slightly bright spots or slightly darker spots have been observed on the surfaces of these very large nearby stars. So yes, the answer is yes for that.
There we go.
How fantastic.
What's the best white light filter to use?
Right. Look, there's a company called Baader, Badder, who make quality solar film, for example, called Safety Film for observing the sun. And from time to time within the solar section, we have a workshop where I will provide some of this safety solar film, and attendees can make their own solar filters to fit over the front of their binoculars or their refracting or reflecting telescopes. So please just keep aware of this opportunity when it comes up. So all materials are provided, and a demonstration on how to make a filter that safely fits over the front of your telescope. So I would recommend Baader safety film. You could go out and buy some yourself, but I think it retails an A4 sheet, sells for about $40. So by all means, come along to a solar section meeting and get some free of charge, okay, as part of your membership benefit. Hey.
I believe that's the film that I used to make the one for the 8-inch Dobsonian we've got here.
Exactly, yes, exactly. Quite right. Now you can buy these commercially, filters that will already fit over the front of your telescope, but you're looking at probably $100 or more for one of these commercially made filters. So you can make one for nothing at a solar section demo. So keep that in mind. How beautiful. Well, what I'm going to do now in the remaining time, because I've only got a few minutes left, is to hunt for one of these prominences and see what we can see from it. So,
you've got probably another 20 minutes, Russ.
have I 20? Okay.
Yep.
Well,
We're only at 7 to 3. In the next session, radio, we slid the radio one back to 3:30. We made a bit of a change there.
okay.
So we could fit some more solar in for you.
Yeah. Well, that's
We've
excellent.
got such a beautifully sunny day.
We have. Now I'm just adjusting the focus now, and you can see focus very, very important to get the best out of it. Look at that. Just gone a little bit past. This is a micro focuser.
Oh, look at that. That's nice.
Right out there, folks. How gorgeous. And as I said, for anyone who's just recently attended, the Earth would fit quite nicely within this little circle I'm drawing on the sun just here.
There we go.
Just to reiterate, and look at these wonderful structures around this area here. Not just sort of amorphous blobs, but there's actual structure associated with these.
Yeah, you can see the swirling nature of it.
Correct. And also for anyone who's just joined, all that motion we're seeing, that is the Earth's atmosphere. It's not actual motions on the sun itself, but it's just simply turbulence in the Earth's atmosphere that's causing the sun to move around a little bit and give it that motion. But nevertheless,
we have another one for you, Russ. How important were the Soho and Parker solar probes for our understanding of the sun?
Well, it's a wonderful question, and thanks for asking it. Incredibly important. Incredibly important. Really, humanity, and I'm speaking for everyone, humanity cannot put a value on the results that these probes have provided and are providing and will provide, because the sun is potentially very, very dangerous to our technology here on planet Earth. Our electrical systems, our orbiting satellites, our GPS. Should the sun give out a huge cloud of ionized plasma called a coronal mass ejection, that could easily knock out our Earth orbiting satellites and destroy our electrical systems here on the ground, and it could cause a lot of issues, far, far worse than COVID-19. So these probes, particularly Soho, are constantly looking at the sun, giving us or giving scientists warning as to what's happening on the sun and whether one of these solar storms is heading our way. Should a solar storm be heading our way, then at least it gives corporations, operators on Earth a few hours in order to put their equipment into safe mode to minimize the damage that a solar storm could cause. And Parker, well, it's going to hopefully reveal an unusual fact about the sun, that although the surface of the sun is only roughly 6,000 degrees, a region above it called the corona is over 1 million degrees. And astronomers can't fully understand why something further from the radiating surface of the sun should be actually hotter than a region below it, because we know that heat travels from hot to cold. So the energy should actually go the other way. But Parker will pass through the inner regions of the corona and hopefully provide data that will help astronomers understand why the corona is so much hotter than the regions below it. So fabulous information for solar scientists, but also for the integrity of our technologies orbiting and on planet Earth.
Okay, so we have a couple more.
Excellent.
Is heat build-up a problem for telescopes even when they're using solar filters?
Once again, a wonderful question, and as I said, it all depends. So these white light filters that go over the front of your telescope, whether it's a refracting telescope, i.e. uses lenses, a reflecting telescope using mirrors, or a pair of binoculars, when that white light filter goes over the front, then that renders that your equipment and your eyes perfectly safe. However, I've got one proviso, that if you have a white light filter and you're going to use it, just make sure it doesn't have any scratches or pinholes in it, because those scratches or pinholes will let full sunlight into your telescope and potentially into your eyes. So if you're going to use a white light filter, always check it. And I check it just by holding it up to the sun. You'll see tiny little pinholes of sunlight shining through. Okay, they appear bright, but they will not damage your eyes in the very, very brief time that you're doing it. But if you put that damaged filter over the front of your telescope and look through the eyepiece, then there's a risk of damaging your eyes. Now, this hydrogen alpha solar telescope, it's actually designed to get a little bit warm inside. The glassware, the beautifully designed filter that filters out, rejects all the wavelengths of light apart from hydrogen alpha. It's designed to get a little bit warm, and it's been designed to do that. And so there's no problem with that at all. But please, everyone, if you bought a telescope kit and it comes provided with a filter that screws over the back of your eyepiece, really deep green glass, throw it out.
Don't use it.
Don't use it, because it is really designed to crack, because that's taking the full impact of all that solar energy, and it'll get very, very hot. And we know that when glass gets hot, it can crack. And should it crack, then your eyes will receive a very short burst of sunlight, and you will end up with eye damage. And so please just throw it out. It's dangerous to use. So hopefully that is the question.
It does. And then there's another one here. We've got a few. We've got about another 3 lined up for you after this one. Paul would like to know, is there a filter or option to show just the corona, similar to when there is an eclipse?
Once again, an excellent question. The answer is no.
There we go, nice and short. It doesn't exist.
For amateurs like ourselves, after all, it's an amateur organization, the only way that we can see the sun's corona with our naked eye or with our eyes is during a total solar eclipse. To see the corona, we actually need to get above, to study the corona, we actually need to get above the Earth's atmosphere, because the corona emits X-rays and a very short wavelength ultraviolet that the Earth's atmosphere absorbs. And it's only a little bit of the coronal light that actually gets through our atmosphere that we see in all of its glory during the total solar eclipse. So, so the answer is essentially no on that.
So we've got a question here from our esteemed radio astronomy section director, Clint Jeffrey. Hi, Russ. Have images of the North and South poles of the sun come through yet?
Once again, a very, very fine question. I'm not aware that they have. I am aware that there is a probe, and its name escapes me, only launched within the last year or so, and that probe is designed to take an orbit which will take it over the sun's north and south poles. I am not sure whether any results have come back as yet, because it naturally takes a while for these probes to get into the correct orbit, but it'll be fascinating to see what the sun's north and south poles actually look like, because from the Earth we don't get very, very good views at all, and there are no probes out there that can help. So a special probe has been launched specifically to fly over the polar regions of the sun, so we can get a good look at it. So excellent question, Clint. Thanks very much.
So roll into the next one. Lee would like to know, how long would we expect to have to view this image here to see movement? Most vision seen from NASA is presumably time-lapse.
Correct.
Are CMEs and flares traveling at tens of thousands of kilometers an hour?
Well, they are, and that's a very, very good question. All I can say is that if we had more time and if we had a large prominence that we could look at, I could have held the video on that prominence, and really I would say over a period of 20 minutes, half an hour, at least or an hour, we would see that prominence change in structure. So that's the sort of time scale that we would be putting at for seeing changes on the sun, changes that that are obvious to our eyes, so to speak. So a period of half an hour or an hour, that period of time. But I would, as I'm talking, I would say that if we could remember all the little blotches that we see on the sun, when we started this, probably 45 minutes ago, half an hour ago, they would have changed between then and now. Just that our memories aren't particularly good for that. But a prominence, because we'll have a set shape associated with it, we would certainly see changes in the shape of a prominence in as little as 15 minutes, particularly if it's the result of a violent explosion on the sun.
All right, we have another one. Thank you for this session. Can you see a solar flare with this setup?
Absolutely. Absolutely we can. Yep. I'm hoping that, well, in fact, we might actually be seeing a flare at the present time. Now, please don't say, oh, Russ Cochran said we were seeing a flare, but this is what we see there. That is what a flare would look like. Just a much brighter area compared with the surrounding areas. But unfortunately, this is a very small sunspot, so any flaring activity would be relatively low energy. But if this was a large, complex sunspot, we might, if we were lucky, because these flares only last for a few minutes, okay, so you've got to be looking to see them. But if we were looking, we would see that sunspot, which would be dark, suddenly become white and overwhelmed, almost disappear, and be replaced by a hot, bright area. So, yep. But effectively, ladies and gentlemen, that white area we're looking at is an indication of what a flare would look like. Okay, a bright white area surrounded by sort of shades of grey.
Okay, so here's another one. Doesn't it take 7 minutes for the light from the sun to reach us?
Well, yes, a little bit longer than 8 minutes and 20 seconds, but I'm a bit of a pedant when it comes to numbers. But yes, so, but very, very true. We are seeing the sun as it was 8 minutes and 20 seconds ago, because that's how long light takes to get to us. And everything, ladies and gentlemen, everything we see in the past, all right, because it takes light a finite period of time to reach us from the sun, star, even from someone sitting next to you. That distance that the light has to travel it will take a finite period of time.
So this next one, I like this one. How do you personally set all this up? Are you under an umbrella or something so you can see the screen? Andrew, he's hiding underneath a towel, which is covering his laptop screen. You guys can't see it, but when Russ is talking, his hands are moving and I can see his screen, and it's very funny. But yes, he's hiding underneath a towel, covering his over the back of the laptop screen so he can see what we're looking at. And
I have the laptop pointing away from the sun.
Yeah, the laptop's pointing away from the sun. Yeah.
Also, we don't want our black laptop to be absorbing all that solar energy and getting overly hot. But yes, unfortunately, Mark's the only one who can see my predicament here. But that's what we have to.
We can show them in a minute. We're probably due to start winding up. One last question. From Sergio, our Brazilian friend who's still hanging around.
Hola, Sergio.
Yeah, he's been. He watched the last stream we had it on, and hopefully he hangs around for the radio astronomy one as well. Russell, last presentation you said the sun had a cycle of 11 years. What causes this 11-year cycle?
Once again, a superb question, and I'll give the same answer I gave yesterday. We just don't know. But
there we go.
But I can elaborate on that it's clearly to do with the internal workings of the sun being a ball of gas. It is very likely that the core of the sun will rotate at a slightly different speed to the outer regions of the sun, and because the sun is a huge magnet, all those magnetic field lines start to get tangled up. As they get tangled up, that releases energy, and that release of energy and that magnetic influence becomes visible in the photosphere and the chromosphere, and hence we see more sunspots. And as I said yesterday, as we learn more about other stars, we are learning that other stars have magnetic cycles as well. Not necessarily 11 years, but therefore we know that our sun's magnetic cycle is not unique. Other stars have magnetic cycles as well.
There we go. All right, I'm going to bring us back on screen with this, Russ, so everyone can see you hiding underneath there now. There we go. Everyone can see you hiding underneath the towel. There you go, guys. That's what he's been doing this whole stream. These
are magnificent views of the sun today.
Yeah. Is it worth checking if some of those prominences have picked up at all before we close it in?
Please do, yes. I'll go back to the full sun. There we are. Look, that's what we're looking at, ladies and gentlemen. I will go to that so we can see the entire sun. Look how
that's
white.
Beautiful, isn't it?
Crank up, absolutely gorgeous. I'll crank up the gain. Look at,
there's a couple there, isn't there?
Here, folks. Oops, sorry about that. I'll cancel that. I've got to go from left to right for these. So we'll just have a look at this region. And take the gain back a little bit, or just... So we've got to find the right medium. So you're getting a little bit of structure in this one. Notice that loop around here. But these are very small, and well, compared with the sun, but as I try to stress, we could probably fit the planet Earth within this little region here of this prominence. And try a little bit of focus.
Oh, Russ, I've just had a message from Linda, and she says there's a KP5 aurora alert for tonight.
Ooh. Well, go for it. Yes, thanks very much, Linda. Thanks for that. So KP5 means that aurorae are potentially visible from southern Australia. Hopefully we have a clear night tonight, although we have a moon in the sky. But if you're not in Melbourne, head to the south coast or head somewhere where you've got a good southerly horizon. Check out an aurora alert app, and good luck with that. Hopefully you'll see some lights in the sky tonight. So bearing in mind, this is all due to solar activity. Aurorae, because of what the sun is up to, and good luck.
Wonderful. All right, so thank you everybody for joining us for this stream. We're going to close this one out now, because in 19 minutes I'll be back again. You have to keep putting up with me, and I'll have the Clint Jeffrey, the radio astronomy section director, and Robert Arrowsmith along to do some radio astronomy with the 8.5 meter dish that we've got. And yes, they have played cricket on it. Well, if you've got a radio dish, you've got to play cricket on it, don't you?
You've got to. Yeah. So thank everyone for joining in. It's been a pleasure.
It has been. Thank you very much for this impromptu solar stream, Russ. It's glad we got some clear skies. So.
And please join the ASV or come along to a solar section meeting, either via Zoom or in person when we can do that.
When we're allowed to, yep.
You can see the sun with your very own eyes.
Wonderful.
Thanks very, very much. Have a good day.
No worries. And we'll also be drawing the Saxon binocular raffles during the radio astronomy section stream. So tune back in about 18 minutes. See you later, guys.
Thanks very much. Bye for now.